In this video, we're going to introduce the concept of transfer functions. So a transfer function is a way of simplifying a circuit or a bunch of circuits or a system or a process. This can be used in a lot of other fields other than just circuit theory. But what it is a way of simplifying an entire mess and saying what's going to happen on an output depending on what your input is. So for us in this class, it's going to be take whatever your output is, we're going to call that y as a phasor, so it's a function of j omega, and then we're going to have the input, which we're going to call x, again in terms of a phasor, x of j omega. These are functions of the frequency omega, and we're simply going to divide these two phasors, output divided by input. That is going to be our transfer function. And the reason why this is going to be so useful is, let's suppose you know what the transfer function is for a given circuit, and you have multiple different inputs, say x1, x2, and so on. And if you want to find all the outputs, instead of having to solve the circuit each and every time, you can just find the output by multiplying the transfer function times the input. And you can do the same thing to find the second output, transfer function times the second input, and so on. So once you've done all the work to find the transfer function initially, you can then find the output for any given input by just a simple multiplication here. Again, this is something that is not going to be just in this class and just basic circuits. It's also this concept is used in a lot of other fields. And it's a very important concept by encapsulating everything that's going on in a single function, where you can find the output by combining it with that transfer function in a simple way, in this case multiplication. That's a very, very useful tool. Now for us, again, since we're just dealing with basic circuits, this is just going to be a fraction involving terms with j omega and then RL and C, depending on the combinations you have. To make life a little bit easier for ourselves, instead of writing out j omega every single time, we will often just replace j omega with the variable s. There is something to that in using s for it, something called Laplace transformation. We're not going to get into that right now, but just for sake of argument, there is a reason why there's an s there and doing it this way. Now, when you combining resistors, capacitors, inductors, you're guaranteed it's going to be a rational function, because resistors, right, the impedance of a resistor is just R. The impedance of an inductor is just j omega L, so for us that's SL. And the impedance of a capacitor is 1 over j omega C, which is 1 over SC. So that's just going to be a rational function involving S here, which we can simplify and write it as a fraction of two polynomials. We have our numerator polynomial and our denominator polynomial. What we're then going to do is we're going to completely factor out these polynomials. So there's going to be some sort of constant at the front, we'll call that k. There's going to be some sort of power of s. It could be a positive power, it could be a negative power, depending on whether the numerator denominator has a higher degree. And then we're going to factor the remaining part in a little bit strange way here. This is our linear term. But instead of saying like s plus 5 or something like that, we're going to write it as 1 plus s over a number. It's mathematically equivalent to do it this way, and we'll see why it's convenient for us to do it that way. But sometimes you're not going to have linear factors. Sometimes you're going to have quadratic factors, and we'll write it in this weird fashion right here. And the denominator, you're also going to have linear and quadratic. And we put the dot dot dots because we don't know how many linear factors there will be. We don't know how many quadratic factors there'll be, and so on. Now, for the linear factors, you see how we have these z's here, because these are going to be giving us zeros of our numerator. And we have our p's here indicating poles of our function. Poles are things that make it undefined. Also, even though you can handle these quadratic terms. I will tell you right now, we're going to really kind of ignore these things. We're only going to deal with the linear terms to simplify things for this class, but you certainly can deal with the quadratic terms as well. Furthermore, it turns out that dealing with h as a transfer function like this is not what's most commonly going to be used to analyze what's going on in the problem. Instead, we're going to be looking at a decimal system for this, a log-based system to handle transfer functions. And in particular, we have this definition here. The decimal transfer function is based on 20 times log of the magnitude of h of j omega. So when we put this here, right, if h itself was like a plus bj as a complex number, then the magnitude would be the square root of a squared plus b squared. Regardless, that's our magnitude. We're going to take 20 log of that. You might ask why the 20? That wasn't my decision. That's part of the historical choice of decibels, how we put a 20 in front of there. Regardless, we'll just assume it's there. One of the great things about using this log scale is logs can be broken up over products and divisions. So what we can do is we can take this big, complicated expression that is our transfer function, and when we apply logs to it, we can have 20 log of just the k, and then n 20 log of just the j omega part from the s here. Then we can have plus and add up all the terms from the numerator, and then minuses for all the terms in the denominator. And by doing this, what we can do is we can see what is just this first term going to do as a result in our problem. And we can analyze just that one term. Then we can say, what is this next one term going to do? And we can add that in. And then what's this next term? So what we can do is we can, instead of trying to figure out from this big, whole complicated rational function what's going on, by doing logs here, we can look at each part separately and simply add the results together. And that's going to make it much easier to try to figure out what's going on in our problem. So now that we have this idea here, next we'll turn into what can we actually do with this. And it turns out we're actually going to eventually draw a graph of this whole messy thing here. And we will see that in a later video.